Chapter 3, Kinematics in 2 dimensions. So this is really just an expansion of Chapter 2. Chapter 2, we got kinematics in 1 dimension, going horizontally side to side, or vertically in the y direction, up and down. Now we're going to put both of those together. It's really hard to do. But you can be rest assured that while the problems will be more complex, they will literally be adding together the individual motions. So that's a really powerful thing, and you want to stay tuned on that. So our first section here, 3.1, is looking at displacement, velocity, and acceleration, and how we can redefine them for 2 dimensions instead of just 1 dimension. So to do that, instead of having just a single x or a y, we're going to use a vector. So we're going to have r naught for our initial position and r for our final position. Again, this is as opposed to just having some x initial and some x final. And then the displacement will be the delta r, the change in r. So the final minus the initial. This is how we can write it for 2 dimensions as opposed to just a single dimension. That's shown here in this figure very nicely. There's the initial position of the race car, and it's drawn as a vector from the origin to wherever we're interested in referring to as our starting point. And then the race car goes around the corner, or most of the corner, and we could draw a vector to its final position from that origin. And the displacement is the difference between these. So it's the shortest distance from the start to the finish. It totally cuts out the whole corner and just says that overall the race car has mostly gone up and very slightly to the right in this case. And so we know with this vector, we could break it down into an x and a y component, right? There is some amount that we could write that there is a delta y that is going up and a delta x that is very slightly to the right. And so the vector is just combining both of those ideas. It's expressing that there's displacement in the x direction as well as in the y direction. All right, now once we have our displacement in 2 dimensions, we can also define our velocity in 2 dimensions. So our average velocity is the displacement divided by the elapsed time. So we can look at our displacement, our change in position in 2 dimensions, divided by our time. Time is just a scalar, so we don't have to worry about the fact that we have multiple directions going. And we can get the average velocity, which, remember, velocity is just telling you the direction that the car has gone on average. So on average, the car has moved up and to the right once again. We can break this down as well into a velocity in the x direction with a vector symbol, plus a velocity in the y direction on average, right? Where it would just be the change in displacement in the x direction divided by the time, delta t, plus the same thing in the y. The change in displacement in y divided by the delta t. And this helps to highlight why chapter 2 feeds so naturally into this, because we've already worked with delta x over delta t or delta y over delta t individually. Now we're just having to consider both of them at once. So this is our average velocity. It doesn't give you at any moment which way it's going, but just say on average going around this turn, the car is mostly going up. Okay, what's often more useful to us rather than the average velocity is going to be the instantaneous velocity. That indicates how fast a car moves and the direction of motion at each instant of time. And it's obtained by taking our definition for average velocity and looking at the limit as delta t approaches 0. So as delta t approaches 0, this becomes smaller and smaller, and this becomes an instantaneous velocity. And actually, there's an error in the slides. There should not be a bar over this. There should be a vector sign, but not that bar. So I'm very sorry about that. I'll try to correct it so you don't have that in the written out slides. But here the picture is very good. So as the race car is going around the turn, kern. You can at any point draw a tangent line to the curve, right? If you have a round object, the tangent line is if you put a flat object against it. Let's find a flat object that doesn't bend. And that flat object would give you the direction of the velocity at any given instant, whatever point it's touching it. So here, as it's going around the curve, the velocity is tangent to that curve, going in that direction up and to the right. And we can break down that velocity into an x component and a y component. And this is the instantaneous velocity. So this is what we'll be using most often. That the instantaneous velocity is equal to the x component of velocity vector plus the y component of velocity vector. So writing that out, vx vector plus vy vector. Now, in general, we won't be able to just add these numbers simply because they are vectors, but we can combine them other ways, right? We notice we can draw the vy over here. Sorry, that's very messy. And we can relate these three sides of the triangle, since this is a right angle, with the Pythagorean theorem. Or we can find this angle theta using our tangent. So we'll have some options there. This will connect back to our chapter 1 ideas, and chapter 1 ideas will help us to combine the horizontal x and the vertical y directions. So this introduces the 2D motion of kinematics that we'll be looking at. Acceleration, we're often going to focus on just that there's some acceleration in the horizontal, some other acceleration in the vertical direction, and that's sufficient for us. So in the next section, we'll look at some equations of kinematics, and then we will get a chance to apply it to a very specific scenario, one of my favorites, projectile motion. So stay tuned, stick around.